Assalamualaikum warahmatullahi wabarakatuh. Hello and welcome to our SCL video for chapter 6. My name is Abdulrazak bin Hasni and my metric number is 225677. I will be covering the introduction to the second law of thermodynamics and thermal energy reservoirs. These two topics are the foundation for understanding how heat and energy work in real-world systems like engines and refrigerators. The first law of the thermodynamics tells us that energy is conserved. It cannot be created or destroyed. However, it doesn't tell us if a process can actually occur. That's where the second law comes in. It introduces the idea of direction. It tells us which processes are possible and which are not. For example, while energy may flow from a hot object to a cool one, the reverse, cold to hot, will not happen naturally. For that, let's look at some examples from our textbook. First, imagine a hot coffee cup in a cool room. It will always cool down and never heat itself. Or consider a paddle wheel rotating when a weight falls. We never see the paddle raise the weight back up by itself. These processes are irreversible and they only go in one direction in nature. The second law explains also why. For the key equation part, there are two main formal statements of the second law. The first one, the Clausius statement, says that the heat cannot flow from a colder body to a hotter one unless work is done. That's why devices like refrigerators or air conditioners need electricity to push heat from a cold space into a warmer room. Without the energy input, it wouldn't be possible at all. For the second one, the Kelvin-Planck statement says that the no-heat engine can convert all the heat it receives into work. There must always be some waste heat release. In other words, some heat must always be rejected to a cold reservoirs. That's why even the best engines like a car engines or a power plants have a limited efficiency. This is also shown in the equation. The thermal efficiency equal to the network output divided by the heat input from the high temperature sources, and it is always less than 1, meaning the efficiency can never be 100%. The second law is also connected to a property called entropy, which measures the disorder of the system. In all natural processes, entropy tends to increase. This is why processes like mixing or heat loss can't be reversed easily. For example, things tend to spread out or cool down. Also, the second law teaches us that not all energy is equal. To high temperature energy is more useful or has higher quality because it can be converted to work more easily. Also, energy from a hotter source has higher quality, meaning it can do more useful work. We use the formula the entropy change equal to Q reversible divided by T, where delta S is the change in entropy, Q is the heat added reversibly, and T is the absolute temperature. A thermal energy reservoir is a body that can absorb or supply large amount of heat without changing its temperature. This is only possible because the reservoir is very large compared to the system. Natural examples include the ocean, rivers, or the atmosphere. In engineering, a hot furnace or a cooling system can also act as a reservoirs. Thermal reservoirs come in two types: a source, which supplies heat, and a sink, which absorbs heat. For example, a power plant receives heat from combustion and dumps waste heat into rivers. This can lead to thermal pollution, where higher water temperature harm marine life. Understanding resolve help us design a cleaner and safer system. And that's all from me. Thank you.
Refrigerator and heat pump. Refrigerator is a special device that transfer heat from a low temperature medium to high temperature medium. It is a cyclic device as it repeats the same process over and over to keep the temperature cool. The working fluid used in the refrigeration cycle is called refrigerant. An example of mostly used refrigeration cycle is vapor compression refrigeration cycle. The refrigeration cycle consists of four steps, which the first one is the compression. In these steps, the refrigerant starts as a vapor and enters the compressor, where it is compressed and becomes hot and high pressure. Next, the condensation process. Refrigerant flows through the condenser coils, usually behind the fridge, where it releases heat to the surrounding air and turns into a liquid, making it then become a high-pressure liquid. The third one is expansion. The liquid refrigerant passes through a small tube called expansion valve or capillary tube, where its pressure and temperature drop quickly. Last but not least, the evaporation, where the cooled low-pressure refrigerant enters the evaporator, usually in the freezer, where it absorbs heat from the inside of the fridge and evaporates. Refrigerant vapor returns to the compressor, and the cycle then continues to keep the fridge cool. Terms to know: QL heat is heat absorbed from inside the fridge, while QH is heat released to the room, and W net in is the network input to the refrigerator. Note that QL and QH represents magnitude and are in positive quantities. Next, the COP are coefficients of performance. The COP of a refrigerator tells us how effectively it removes heat from the cooled space using work input. The basic formula is QL, which is desired output, over by W net in, which is work input. This relation can also be expressed in rate form by replacing QL by Q dot L and W net in by W dot net in. The conservation of energy principle for a cyclic device requires that W net in is equivalent to QH minus QL. Therefore, the new formula is COPR is equals to QL over by QH minus QL. Please note that COPR can be greater than 1, which means that the fridge can remove more heat than the work it consumes. This is in contrast to the thermal efficiency, which can never be greater than 1.
Heat pump. What is heat pump? Pump is a device that transfers heat from a colder place to a warmer one by doing external work. At first glance, the heat pump and refrigerator seems like the same, and that is correct because they are the same. In a refrigerator, the goal is to keep the inside cool, so the heat is taken out and dumped into the room, while in a heat pump, the goal is to heat the room, so it grabs the heat from the cold outside air and delivers it inside. How does the heat pump works? There are four main components in heat pump. First is evaporator coil. It is used to absorb heat. Second is the compressor. It is used to compress refrigerant. Third is condenser coil. It is used to release heat. And lastly, expansion valve. It is used to reduce pressure for cooling. The heat pump absorbs low temperature heat from outside air and then compresses the refrigerant using a compressor, and then it releases a high temperature heat inside the house. For heating mode, the refrigerant absorbs the heat from the cold outside air in the evaporator coil. Then it goes to the compressor, which increases the pressure and makes it hot. Then the hot refrigerant releases heat into the house through the condenser coil. Then it passes through the expansion valve to cool down and the cycle repeats. Coefficient of performance, COP. What is COP? COP is a measure of how efficiently a heat pump uses energy to move heat from one place to another. The formula for the COP of a heat pump is COP equals to heat divided by work. For example, if the COP of a heat pump equals to 3, it means for 1 unit of work, the heat pump delivers 3 units of heat into your home.
Lastly, let's go over some questions to get a clearer understanding. Question 1. Determine the COP of a heat pump that supplies energy to a house at a rate of 8,000 kJ per hour for each kilowatt of electric power it draws. Also, determine the rate of energy absorption from the outdoor air. Step 1. Understand the COP formula. For a heat pump, COP-HP is equal to QH over WIN, where QH is heat delivered to the house in kilojoule per hour, while WIN is work input converted to kilojoule per hour. Step 2. Unit conversions. Since power is given in kilowatt, convert it to kilojoule per hour. 1 kilowatt is equal to 1 kilojoule per second, which equal to 3600 kilojoule per hour. So, W input is equal to 1 kilowatt, which is equivalent to 3600 kilojoule per hour. Step 3. Calculate COP. COP of heat pump is given by QH over W input. So, 8000 kilojoule per hour is divided by 3600 kilojoule per hour, and the answer is 2.22. There is no unit as the unit has cancelled each other. Step 4. Energy balance to find energy. Given QL is equal to QH minus W input. So 8000 kilojoule per hour minus 3600 kilojoule per hour, and we got 4400 kilojoule per hour. The coefficient of performance is 2.22 and energy absorbed from outdoor air is 4400 kilojoule per hour. Question 2. An air conditioner removes heat steadily from a house at a rate of 750 kilojoule per minute while drawing electric power at a rate of 6 kilowatt. Determine A. the COP of this air conditioner, and B. the rate of heat transfer to the outside air. Step 1. Convert electric power to kilojoule per minute. Since W input equal to 6 kilowatt, convert to kilojoule per minute. 1 kilowatt equal to 1 kilojoule per second, which is equal to 60 kilojoule per minute. So, 6 kilowatt times 60 is equal to 360 kilojoule per minute. Step 2. Calculate COP. Formula for COP of an air conditioner. COP AC equal QL over W input. Substitute the value 750 divided by 360, and the answer is 2.08. Step 3. Calculate rate of heat transfer to the outside air. Given the energy balance is QH equals to QL plus W input. So 750 plus 360, and we get 1110 kilojoule per minute. So the answer for A, COP, is 2.08, and B, rate of heat transfer to outside air is 1110 kilojoule per minute. Question 3. Bananas are to be cooled from 24 to 138 degrees Celsius at a rate of 215 kg per hour by a refrigeration system. The power input to the refrigerator is 1.4 kilowatt. Determine the rate of cooling in kilojoule per minute and the COP of the refrigerator. The specific heat of banana above freezing is 3.35 kilojoule per kg degree Celsius. Step 1. Calculate rate of cooling Q.L. Given formula of Q.L is m dot times Cp times delta T. Convert mass flow rate to kilogram per minute. M dot is equal to 215 kilogram per hour over 60. And we get 3.5833 kilogram per minute. Then calculate Q.L. Q.L is equal to 3.5833 kilogram per minute times 3.35 kilojoule degree Celsius times 11 degree Celsius, and we get 131.93 kilojoule per minute. Step 2. Convert power input to kilojoule per minute. 1 kilowatt is equal to 60 kilojoule per minute. So W input given 1.4 kilowatt times 60, and we get 84 kilojoule per minute. Step 3. Calculate COP of refrigerator. Given the COP of refrigerator is Q.L over W input. So 131.93 divided by 84, and we get 1.57. The answer for A, rate of cooling, is 131.93 kilojoule per minute, while B, COP of refrigerator is 1.57.